What is the quadratic form? Today I will discuss principal axis theorem. This theorem is actual idea is consider two quadratic form, and notice this type of quadratic form is difficult because here D, E, F this term also exists, but here only ax square bxy plus cy square. So by this quadratic form it is not clear what would be the graph of above function. So we now apply the change of axis, and by principal axis theorem we can tell change of axis directly simplify the situation. Change of axis reduces this type of situation ax square bxy plus cy square. Then we can verify what would be the conic, what would be the graph of the conic. Okay, we all of us know every quadratic form can be written as x transpose x, where a be many form, but every quadratic form actually can be expressed as a real symmetric matrix A, where x is the column vector x, y, z. So obviously x transpose means row vector x, y, z. As for example, consider 2x1 square plus 10x1 x2 plus 2x2 square equal to 1. Consider this transformation as x transpose ax equal to 1, where obviously a equal to 2552. So obviously this is actually the quadratic from x transpose ax equal to 1. Now my question, by principal axis theorem evaluate how would be the graph of this conic. Actually we all of us know the idea of orthogonal matrices. Let P be square matrix with real components. We say that P is orthogonal if P transpose equal to P inverse. Because for orthogonal matrices P transpose P equal to identity which is equal to P transpose. Now if P will diagonalize our real symmetric matrix A in the sense P inverse AP which is equal to actually P transpose equal AP equal to diagonal T, and this matrix is diagonal matrix means lambda 1 0 0 0 lambda 2 0 0 such type, where lambda 1 lambda 2 and lambda n equal to actually the eigenvalue, and the proof is such type AP equal to, since P is orthogonal matrix, so consider P be the eigenvector of the matrix A, then this would be such type AV1 up to AVN which is equal to actually AV1 up to AVN, and AV1 means obviously lambda 1 V1, AVN means obviously lambda n Vn, which is actually equivalent to P times lambda 1 0 0 0 lambda 2 0 0 0 0 lambda n, and this term is actually AP equal to PD. That implies P inverse AP equal to diagonal D, and since P is a orthogonal matrix, so obviously P inverse AP equal to diagonal D. Okay, and this is the actual idea of the diagonalization. Here P, the matrix P will be diagonalize our real symmetric matrix in the sense of P inverse AP equal to diagonal matrix D. We all of us know this is the idea of diagonalization. In my previous video I have defined this topic elaborately. Actually today I will use this concept again. So I have, as I recall, mentioned this part again. Now let's come back our original question. Here we have to find by principal axis theorem what would be the conic. Here I will use this concept principal axis theorem. For this I will just diagonalize A and the concept would be such type A equal to PDP inverse, where obviously D means the diagonal matrix whose diagonal be only the eigenvalue of the matrix A, and obviously the eigenvalue of the matrix is such type lambda 1 equal to 7 and lambda 2 equal to -3. So D equal to 7 0 0 -3, and P would be just eigenvector, and the eigenvector of A would be 1 1 and -1 1. But since the matrix is symmetric, so these diagonalize can be orthogonally diagonalize A, and the idea is here A equal to PDP transpose, where obviously D means 7 0 0 -3 this eigenvalue, and by Gram-Schmidt method here the idea is here P would be such type, here each eigenvector P would be such type V by norm V, sorry here V, consider V1, here consider V2 by norm V2, V3 by norm V3, V4 by norm V4. Okay, P would be such type. So the matrix P would be 1 over square root of 2 minus 1 over square root of -2 square root of 2, 1 over square root of 2, 1 over square root of 2. And here the idea is x transpose A, x equal to, obviously A means PDP transpose, by orthogonal diagonalization we can tell. Here this quadratic form would be transformed new quadratic form, and this is actual idea of principal axis theorem, because x transpose P we can write this as P transpose x transpose D P transpose x. Now for easy calculation consider this P transpose x equal to y, then x transpose x reduces y transpose dy. I hope my all viewers have understood this concept easily, where obviously y means P transpose x, that means y means y1 y2, and P transpose means obviously P means this matrix, so P transpose means this matrix times x1 x the column vector x1 x2, then this reduces to y1 equal to 1 over square root of 2 x1 plus 1 over square root of 2 x2, and y2 equal to minus 1 over square root of 2 x1 plus 1 over square root of 2 x2. That means from this line, this is this point be minus 1 over square root of 2 comma 1 over square root of 2, and here the point is 1 over square root of 2 comma 1 over square root of 2, and consider this is actually the principal axis. Then this quadratic form reduces since y transpose dy, that means 2x1 square plus 10x1 x2 plus 2x2 square equal to, we can write this as x transpose ax, and this is reduces to y transpose dy, where y means obviously the row vector y1 comma y2, y transpose means, and D means the only diagonal 7 and minus 3 eigenvalue of this matrix, and here y1 y2. That means this is reduces to this conic 7y1 square plus 3 minus 3y2 square equal to 1, and obviously this is hyperbola. That means this, by principal access theorem, we can tell this is reduces to hyperbola. Actually, the principal access theorem is, let A be real symmetric matrix with eigenvalue lambda 1, lambda 2, lambda n, and if we from the orthogonal matrix P equal to v1, v2, vn, obviously this v1, v2, vn means obviously the eigenvector, then substitute x equal to py, and after substitution transform the quadratic from x transpose ax to the principal from y transpose dy, which is actually lambda 1 y1 square up to lambda n yn square. This is the principal axis theorem. I hope my all viewers have understood this concept easily. Okay, I will see one application of principal axis theorem. Consider the quadratic from q equal to 3x square plus 2 square root of 2 square xy plus 4y square. Obviously this quadratic form is written as q equal to x transpose ax. Here the matrix A equal to 3 square root of 2 square root of 2 4, and consider q equal to 1, and notice here the matrix A is symmetric matrix. Then by principal axis theorem we can tell q represent as lambda 1 y1 square plus lambda 2 y2 square. By principal axis theorem we can tell this. And obviously this lambda 1 and lambda 2 be the eigenvalue of this matrix. So at first find the eigenvalue of this matrix, then we can tell in which graph by principal access theorem this quadratic form reduces. After calculating, I have got the eigenvalue of this matrix be 5 and 2. So this quadratic form transform to 5y1 square plus 2y2 square, and in the question has given q equal to 1. So obviously q equal to 1, that means this quadratic form actually reduces to 5y1 square plus 2y2 square equal to 1, which is actually the picture of ellipse, and the picture would be such type. The picture, this is the picture of this ellipse, and by principal axis theorem we can tell the original picture of this theory of this quadratic form would be, here the principal axis lie on the eigenvector. So at first find the eigenvector. For lambda equal to 5, I will get v2 equal to square root of 2 v1. Consider v1 equal to 1, then v2 would be square root of 2, and then consider the eigenvector is v1 cap, then this would be 1 square root of 2. And obviously at first we all of us know for principal axis theorem we have to take those eigenvector which is actually unit in norm. So just divide by norm. So this would be 1 over square root of 3 times the vector 1 square root of 2. Similarly, if we consider the eigenvalue lambda equal to 2, then the eigenvector would be v2 cap, which would be minus square root of 2 and 1. Since this is, we have to divide this as norm. So V2 perf would be 1 over square root of 3 minus square root of 2, 1. This is the V2 perf. That means this is actually V1 and this is V2. And this is actually the principal axis. And since here actually this is reduces to ellipse, where this is the x-axis and this is y-axis, but here this ellipse would be in these two axes, so ellipse would be such type. That means by principal axis theorem we can tell this ellipse reduces to after rotation in this ellipse. I hope my all viewers have understood this concept easily. Okay? Well, just recall the definition of congruent. We all of us know A and B, two matrix A and B, which is square matrix of order n. B is congruent to A if B equal to P transpose AP for some non-singular matrix B. Then that imply A is congruent to B. That means that imply A and B are congruent. Actually, congruence is more general concept than similarity of symmetric matrix by an orthogonal matrix P. And in quadratic form, by principal axis theorem, the quadratic from x transpose AX is equivalent to y transpose BY, which is actually lambda 1 y1 square up to lambda n yn square, where obviously the matrix B equal to diagonal along diagonal lambda 1 lambda 2 up to lambda n, and other part would be 0. That means obviously here the matrix A is congruent to matrix B. By principal axis theorem we can tell. And when Qy greater than 0, that means obviously all lambda 1 lambda 2 up to lambda n would be greater than 0, then the matrix is positive definite matrix, we all of us know. And when Qy less than 0, then lambda 1 lambda 2 up to lambda n would be less than 0, all eigenvalue would be less than 0, then this is the negative definite. And when eigenvalue are both positive and negative, then these are indefinite. We all of us know this part. And positive semi-definite, if there exists one eigenvalue or one more eigenvalue which be 0, then this would be positive semi-definite. Similarly, for negative semi-definite means if there exists at least one eigenvalue which is 0, then this would be negative semi-definite. Similarly, quadratic form is equivalent to a quadratic form y1 square plus y2 square plus yp square minus yp plus 1 whole square minus yp plus 2 whole square up to yr square. Then notice here there exists p times positive eigenvalue and r minus p times negative eigenvalue, and rank of this quadratic form is r. There exists a nice concept, inertia. This is actually concept how many eigenvalue be positive, how many eigenvalue be negative, and how many zero eigenvalue exist. And the difference between number of positive eigenvalue and negative eigenvalue is called signature of the quadratic form. And the notation is, if number of positive eigenvalue is p, then obviously if r be the rank of the matrix, then r minus p would be negative eigenvalue. Okay. Then signature means difference between number of positive eigenvalue and negative eigenvalue. Then this value would be p minus r minus p, which is actually 2p minus r. That means signature is equal to actually 2p minus r. Now I will see nature of one quadratic equation. This is the given quadratic equation. Obviously this quadratic equation represents this matrix, which is obviously symmetric matrix. Then the question, find the nature of the quadratic from. Nature means what is the rank of the matrix, signature of the matrix, and index. Here index is new term. Actually index means number of positive eigenvalue. Just answer what would be the eigenvalue. The eigenvalue would be actually 0, 1, 3 of this matrix. Therefore, by principal axis theorem we can tell this quadratic form represent 0 lambda 1 square plus lambda 2 square plus 3 lambda 3 square. This quadratic form by principal axis theorem reduces in this quadratic form, we all of us know. Therefore, rank means number of non-zero eigenvalue. Since here number of non-zero eigenvalue is 2, so rank is 2. Index means number of positive eigenvalue. Since notice here number of positive eigenvalue is 2, so index is 2. Signature means obviously signature, the definition is 2p minus r, where obviously p means number of positive eigenvalue and r means rank. Then this would be 2 times 2 minus 2, 4 minus 2, which is equal to 2. That means the value of signature would be 2, the value of index would be 2, and the value of rank would be 2. I hope my all viewers have understood how we have to find nature of any quadratic form. Okay? This type of concept actually very important for higher study, also for any competitive exam. Today I will stop here. In my next video I will discuss this topic also elaborately, because this type of concept actually very important for every competitive exam. Also in my next video I will see when two or more quadratic form be equivalent. Okay? See you soon. Stay safe and stay positive always. And don't forget to subscribe my channel for more videos. Thank you so much.